Ideal gas examples. We will now look at some examples of application of the theory of ideal gases. The first example, 1 mole of an ideal gas has a temperature of 17 degrees centigrade and a volume of 4.85 liters. Find its pressure. First, let's convert the temperature to Kelvin. That's 273 plus 17, 290 Kelvin. You must have Kelvin for using the ideal gas law. N is one number of moles. All we do is take the ideal gas law and solve for pressure P, and we find out that it's 497 kilopascals. Example 2. Find the internal energy of a monatomic ideal gas in the state of example 1. Well, a monatomic ideal gas has U equals 3 halves nRT, and if we put in the numbers, we find 3,617 joules. Or because we know that PV equals nRT, we can find that U equals 3 halves PV, and again 3,617 joules. Example 3. In a process, 1 mole of an ideal gas has initial pressure 165 kilopascals and initial volume 4.35 liters. It first expands isobarically to 7.84 liters, and then its pressure decreases isochorically to 121 kilopascals. Here is a PV diagram showing the process. The gas starts on the left at the top at 165 kilopascals at pressure P1 and volume V1. It follows the horizontal line constant pressure isobar, that's path A, and then goes down in path B in the isocore, which is the constant volume process. A. Find the work W done in the process. Now, work is only done in path A because in path B, being an isocore, no work is done. The work in the isobaric process is easy to calculate. It's P1 times V2 minus V1, and we find that it's plus 576 joules. V2 is bigger than V1, and we know that it's an expansion where the gas does work. Part B. Find the change in temperature. In state 1, the initial state, from PV equals nRT, we can solve for T1 to find 86.3 Kelvin. And we do the same for state 2, the final state, and we find that's 114.1 Kelvin, and the difference is delta T equals T2 minus T1, which is equal to 28 Kelvin. In part C, what is delta U, the change in internal energy, if the gas is diatomic? Well, we know that U is equal to 5 halves nRT, so we know that delta U equals 5 halves nR delta T, and putting in the numbers, it's 582 joules, an increase in internal energy since the temperature has increased. Part D, in the case above, also diatomic, find the heat added. Well, from the first law we know delta U equals Q minus W. Q equals delta U plus W, which is plus 1,158 joules, so positive heat is added. Part E, also for the diatomic case, find Q prime for a different process with A and B reversed as shown in the diagram. In this case, W prime is now P2 times V2 minus V1, which is 442 joules. Delta U is the same. Remember, it does not depend on the path. So this time Q prime is equal to delta U plus W prime, which is 1004 joules. It's different to Q in the first path. Example 4. 5 moles of an ideal gas are compressed isothermally from V1 equals 8 liters to V2 equals 4 liters at T equals 300 Kelvin. How much work is done on the gas? And how much heat Q is added to the gas? What is delta U in the process? We know that the work done by the gas is equal to minus the work done on the gas, and the work done by the gas is equal to nRT log V2 over V1, which is equal to minus 28.8 joules. Therefore, the work done on the gas is plus 28.8 joules. Delta U is 0 since T is constant. Therefore, Q equals delta U plus W by, which is equal to minus 28.8 joules. So 28.8 joules are lost from the gas. Example 5. The same gas as in example 4 is now compressed adiabatically from the same initial state to a final state with V2 equals 4 liters. Find P2. Assume that the gas is monatomic. From PV equals nRT, we know that P1 equals nRT1 over V1, and we find the pressure P1, which is 1.56 megapascals. Note that gamma is equal to 5/3 for a monatomic gas, and use PV to the gamma equals constant. So P1V1 to the gamma equals P2V2 to the gamma, and we solve for P2, which is equal to P1 times V1 over V2, all to the gamma, and putting in the numbers, we find that P2 is 4.95 megapascals. Here is a PV diagram showing the adiabat. Note that for the isotherm, the pressure is 3.18 megapascals at the same final volume, which is lower than that of the adiabat. That's because when the gas is compressed adiabatically, energy is added to it and its internal energy goes up and its temperature goes up, so its pressure goes up.